Welcome to lecture 53. This is week 11 and in this week we are talking about applications of optimization. So, as of now we have seen certain examples from chemical engineering and solve those optimization problem using MATLAB's optimization toolbox. So, we have now become familiar with some of the functions that are available in MATLAB optimization toolbox. In today's lecture, we will learn one more function known as fmin BND. fmin BND solves a minimization problem of a single variable function and the optimum is located in a fixed interval. That means, you know the bounds on the decision variable. So, let us see how we can solve a minimization problem in single variable using fmin BND. So, the MATLAB function fmin BND finds minimum of a single variable function on fixed interval. Here x1, x2 are finite scalars and fx is a function that returns a scalar. So, basically we have a single variable function and we are going to find the minimum of the function in the fixed interval x1 to x2. x1, x2 are all scalars and fx is a function that will also return a scalar value. So, this is the syntax for fmin BND. X equal to fmin BND and the arguments are fun x1, x2. So, the fun is the name of the function where you define the objective function and x1, x2 are the lower bound and upper bound on the decision variable. So, basically it solves minimization fx and x is bounded between x1 and x2. You can also supply the options argument to give instruction to fmin BND for additional work, such as you may like to display the values that are being obtained at each iterations. Now, so this syntax tells you that not only you get the final solution, but you also get the function value, that means value of the objective function computed at the solution x. You can also have as an output exit flag, which describes the exit conditions, how the optimization was terminated. And finally, you may also have a structure called output as output variable, which will contain information about the optimization. So, the output structure will tell you about the informations on the optimization, how many function values were required, what algorithm was used, so on and so forth. You can obtain more information about the use of fmin BND in this MATLAB website. Fmin BND uses an algorithm that is based on golden section search and parabolic interpolation. So, the algorithm on which Fmin BND works is based on golden section search and parabolic interpolation. Certain points to be noted about Fmin BND. The function to be minimized must be continuous. Fmin BND may converge to local solutions. Fmin BND can exhibit slow convergence when the solution is on a boundary of the interval. In such case, Fmin_con often gives faster and more accurate solutions. Now, let us take a simple example to understand the use of the function Fmin BND. So, we want to minimize a function f x equal to x square minus 2 and x is bounded between minus 2 and plus 2. So, this is the problem we want to solve using Fmin BND. You can find out the solution by just looking at the problem. The minimum value that the function will have is when x equal to 0. In that case, function value will be minus 2. Note that the function value cannot go below this, because x square is always a positive term. So, the minimum value will be minus 2 and that corresponds to the value of x equal to 0. So, let us see whether we get this solution using Fmin BND. So, as usual, we have to first write a function file to evaluate the objective function. So, that is the argument fun. So, you need first to write a function file where you will define the objective function. So, you have to follow the rule of writing a function, and this is how you write the function file. Function f equal to myFun argument x. So, name of the function is myFun. So, within this function I define the objective function f equal to x square minus 2. So, this function receives x as input and sends f, which is the objective function value, as output. Now, we are ready to call the Fmin BND optimization solver for minimization. So, you can define options equal to optimset display iter. So, it will display the output at each iteration and then use the syntax to call Fmin BND. So, the output will be x and fval, that means the solution as well as the function value at this solution. Note how this name of the function is being supplied, minus 2 is the lower bound, plus 2 is the upper bound on the decision variables and the options. So, this is how you will call the optimization solver. You can write this 2 lines on MATLAB command window. Before that, of course, you will create a function file and save this, and then either you can write these 2 lines on the MATLAB's command window, or you can write another script file and write these things, save this and then run. So, this is what you get as solution. Since we have opted to display the output at each iteration, the MATLAB sends you the output at each iteration. And these are the algorithms that has been used at various iterations. It started with golden section search and then later on moved to parabolic interpolation. So, this is actually a very efficient way of doing one dimensional search. You can start with a golden section and then move to cubic interpolation or parabolic interpolation. FMIN BND uses golden section search and parabolic interpolation. So, the solution that we get is minus 5 into 10 to the power minus 7. So, this is almost 0, and the function value as expected is minus 2. It is a single variable function. So, you can simply plot this function as we have done here, and you can locate the minimum at x equal to 0, corresponds to f x equal to minus 2. So, obviously, you get the same solution. Now, there is an alternate use. Look at the previous way of calling the solver, and particularly look at this argument at my fun. So, this is the function which contains the objective function value. So, the myfun computes the value of the objective function at decision variable value x and supplies it to FMIN BND solver. Now, alternately, what we can do is the argument fun can also be a function handle for an anonymous function. For a simple function like this f x equal to x square minus 2, I can define f as shown, f equal to add x then x square minus 2, and you can now write this f here. You can also write this here. So, this is sometimes convenient if you have a simple function. Obviously, if you have a complicated functions, you will define a function file like myfun and save it as myfun.m and then follow the syntax that we have seen in the previous slides. So, now let us try to solve some of the problems that we have already solved in lecture 51 using solvers such as fmin search and fmin con. So, the first problem that we take is optimum number of reactors in a reactor train. So, we have n number of CSTRs in series in a reactor train. We want to find the optimum number of CSTR that minimizes the total cost. So, you can go back to the slides of lecture 51 and can see the optimization problem formulation. Please recall that we are able to express the total cost as a function of n, where n is number of CSTR in the series. So, as n changes, the cost changes, and given the data and information, we are able to express the cost as a function of n. So, the total cost is now function of single variable n, which is the number of CSTR units. So, we should be able to solve it using fmin BND. Of course, you have to put a lower bound and upper bound. So, let us look at the MATLAB codes that you have to use. So, first write the function file for the objective function. So, we will define a function known as cost. You can define by any other name you like. So, we define a function called cost, which takes n as input. N is nothing but my decision variable, number of CSTR units in the reactor train. So, this is the expression of the cost. So, for given value of n, this function will be able to find the cost which is contained in C, and it will be returned to the solver fmin BND. Now, we are ready to call fmin BND solver for optimization. So, again you can write these statements on MATLAB command window, or you can create a script file where you enter these statements, save it, give a name and save it, and then run that file. So, x1 equal to 1 and x2 equal to 10. So, basically we consider n is bounded between 1 and 10. Then we use options to display the results at each iteration, and also the tolerance value is set at 10 to the power minus 8. and this is the syntax we use now to call f min BND. So, the what f min BND will return is n, which is the solution, that is number of CSTR units that minimizes the total cost, and f val, that means the cost associated with this optimal number of CSTR units n. So, arguments for f min BND: at cost, this is the function file that will evaluate the cost. X1 is lower bound, set as 1 here, X2 as upper bound, set as 10 here, and options. Then we just print the results. So, the result that you get is n equal to 4.127203, and the optimal cost is 37,17,878. So, we got result very similar to this earlier when you use f min search. So, the optimum number of reactors can be taken as 4, and then you can compute the volume of each CSTR as 120 meter cube. So, this is the output of f min BND. The function count was 12, and the algorithms, again it started with golden section search, then moved to parabolic, then again it used golden section search, and finally completed with parabolic interpolation. So, if you compare the result that was obtained with f min search, the results are here. N equal to 4.127214 was the result that we obtained with f min search, and here we get 4.127203. So, up to 4 places after decimal, the results are same for value of n. Same thing for the value of the optimal cost. Now, as a second example, again let us revisit lecture number 53 and solve again the problem on optimal pipe diameter. Again, that was formulated as a single variable optimization problem. Look at lecture 53 for the problem formulation, which is reproduced here. The cost has been expressed as a single variable function of pipe diameter d by this long expression, and the optimal pipe diameter has upper bound as 6 and lower bound as 2.5. So, this can also be solved using f min BND, because it is a single variable function and we know the bounds on the optimal pipe diameter. So, to solve using F-min BND, you first have to define the function file where you will evaluate the objective function. So, this is true for all the functions that we have used so far. Syntax is very much similar. So, we create a function file called pipe dia, which takes one input, which is d, and this stands for the diameter of the pipe. The length of the pipe and flow rate, they are all specified. Please look at lecture number 53. And then you can compute the cost corresponding to pipe diameter d. So, now once we have written the function file that will evaluate the objective function, we are ready to call the F-min BND solver. So, again you can either write these statements on the MATLAB command window, or you can create a script file, write these statements, save the file. You have to give a name. So, it will be your name.m file. You have to run that file to get the solution. So, D1 is 0.25, D2 is 6, upper bound and lower bound, options, and then the syntax we are following is D and F-val are the values that F-min BND will return, function file at pipe dia, D1, D2, lower bound and upper bound, and options. And then you also print the optimal cost. So, the solution that you get is D equal to 0.825048, and the optimal cost associated with this pipe diameter is 796.649326. So, this is the output of F-min BND. The function count was 14. It started with golden section search, moved to parabolic, again used golden section search, and then finally completed it with parabolic interpolation. In our previous lecture, we solved the same problem using F-min con, and again note that the values that were obtained, they match up to 4 places after decimal. Since this was a single variable function, you can of course plot the cost function with respect to pipe diameter and can check for yourself the optimal solution lies around 0.8. So, the true optimal solution as computed using F-min BND is 0.8250 inch. So, this is how we can solve a single variable minimization problem where we know the optimal solution lies between a lower bound and an upper bound. So, with this we complete lecture 53 here.